And we want to look at questions here that we use what we call a reduction formula or a recurrence formula to basically use the function back in on itself. And the ones we see here, we can't get a integral straight out for it. So, but we can manipulate it such that we will be able to get a relationship that we can use and use as the integral. Now, only certain types of functions will do this, and we just got to take a bit of care with our notation and seeing where the function exists. So what we want to do here is, first one we're starting off with is we've got a function that is cos x to the power of n between 0 and pi on 2, and we want to break it down that basically the integral itself would be n minus 1 over n, depending on whatever n was there, times the integral, but where the power of the cos x would be n minus 2, so 2 down from whatever that value is. So, and we can see how we can start to use it to break it down and be able to get a value here for our definite integral. So, we're going to use the term in all the way through, and that's why you notice that it stays there on the left hand side, because it's important to our notation. So, we going integral of between 0 and pi on 2 of cos of x to the power of n. We want to integrate this by parts, so we're going to break it down to cos of x and cos of n minus 1x. So we'll integrate our first, leave our second. So that's where we get that part in there. And we're going to integrate our first and leave our second. So we see that, derive our second. So that's where we're getting this part here. So sine of x, n minus 1, cos of n, power of n minus 2x, times minus sine of x. So this is where the sine squared x comes in. We've got a positive n minus 1 there, with the cos of power of n minus 2. Now we want to manipulate this, so because the sine squared x isn't going to help us too much. The first part, if we put our values in, well, when we put pi on 2 in, cos of that would be equal to 0, and when we put the 0 in, sine of that would be equal to 0. So that's going to come down to 0 there. So that part there comes down to be 0, which is not too bad because that cleans it up. And we get the n minus 1. We've got a change from sine squared x to 1 minus cos squared x. And then we can expand that bracket. We get the n minus 1 between 0 and pi on 2 of cos of n minus 2x. And also the n minus 1, because it's cos squared, cos n minus 2, we get cos x to the power of n. Now, hopefully we're looking and going, well, wait on, that's what we started with. So we could write it back in this notation. The in, so the integral here, is n minus 1 of the integral, except it's to the power of n minus 2. And we've got the cos of power of n, which is going to be in again. Which means that if I add this on both sides, because that's 1, I've got the minus n plus 1, so I'm going to subtract 1, I'm going to add n. That gives us the n times in on this side. And we're leaving with the n minus 1, in minus 2 there, and then divide by n gives us the result we need there. So there's our manipulation. We get it back to something in terms of cos n and cos of n minus 2, which allows us to then evaluate cos x to the power of 7. Because if we use the formula, basically we're going to use this formula all the way through and say, well, 6 over, that'd be 6 over 7, because n minus 1 over n, times I5. And then I5 would be n minus 1, so 5 minus 1 over 5, I3, and I3 would be 3 minus 1 over 3, I1. Now, we get to the point where we've got I1, and we can actually calculate that, because that's just cos of x to the power of 1, be sine of x between pi and 2 and 0, which is 1. Which means that we can have the the I5 would be 4 on 5 I3, and I3 was 2/3 of I1, and I1 ends up being 1. So 6 on 7 times 4 on 5 times 2 on 3 gives us 16 on 35. So there's that manipulation. We because we were able to break it down all the way, it then ends up being something really nice. This time we've got sec x tan x to the power of n. So find I1. So we're doing the easy part first. So substitute 1 in, so we get sec x tan x, which integrates to sec x between 0 and pi and 4. So sec of pi and 4 minus sec of 0 gives us 1 on 1 minus 1 on root 2, which will clean up to root 2 minus 1. So obviously we're going to use that later. We want to prove that in can be root 2 on n minus 1 on n I of n minus 2. Well, let's start manipulating. So we break the function down to sec x tan x and tan n minus 1x. So we've decomposed tan of x, because if we integrate sec x tan x, that will give us sec x. So we integrate this function. We're taking this one as our first function and leaving our second, and then integrating our first. So it comes to sec x nicely every time, and differentiating our second. So the n minus 1 tan of n minus 2 times the derivative of derivative of tan, which would be sec squared x, which we can start to manipulate. We'll leave our left hand part here. We bring the n minus 1 out and convert sec squared x to 1 plus tan squared x, which we can then expand with our product here to give us sec of tan n minus 2x plus sec x tan x to the power of n, which we can start to write in this notation again. So we can do the calculation of this first part. That comes down to root 2 times 1 minus 0. And we get minus of n minus 1 times in minus 2, and minus the n minus 1 of in, which again we can start to take across to our left hand side, because we can collect our terms in in, and that cleans up to n of in. We've got our root 2, and we've got n minus 1 on in n2, and then divide by n gives us root 2 on n, the n minus 1 on n, I of n minus 2. So there's our function there we wanted to get. And then evaluate I5. So again, we put in our root 2 on 5. We're using this rule. And n minus 1 on 5, I of n minus 2. And I3, root 2 on 3, 2/3 of I1. And then I1 from part 1 we knew was root 2 minus 1. Put that all together. So we're substituting I1 into there, and then taking all that and substituting it into there, gives us that expression, which we can start to clean up and get our answer that we wanted there. So that's how the formula starts to work. We start to manipulate it and get it down to something that we can use, and have it recur back on itself, or reduce down to something that we can put into an expression to simplify it. Even though it looks like we haven't completed our integration, we've just manipulated to give us an expression for the integral in a little bit of a different way.